Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. We are discussing about deep visual learning and we will continue that discussion. In the last lecture, I discussed several components of a deep learning neural network for which this kind of visual learning takes place, or processing of visual information, visual images, those take place. We talked about the feature extraction part, and there we have seen that we have discussed that there are two, particularly there is a convolutional layer, a particular type of neurons which performs the convolutions at a point of the image, and like the convolution operations over an image, similarly the neural network, it performs the convolution operation given a set of or given an image, and this layer is called convolution layer. And then there is also another layer which reduces the number of samples, or which downsamples the image, and we call that layer as pooling layer. So these two layers we talked, and which in a combination of them, a cascaded series of this processing converts an image into a feature representation, extracts those features in stages along the multiple layers. It's like, once again, feed-forward neural network. And then these features, they become, finally, at the end of this processing, we get a feature representation, which is further fed into the classifier. Again, it is in the same form of artificial neural network, what we discussed earlier. That's the fully connected feed-forward neural network. So this layer is called fully connected layer, and it performs the classification task. Like the artificial neural network, there could be several such fully connected layers which are acting like an hidden layers, and finally there is an output layer from where the corresponding functional values, target functional values for each node, output node, are computed, which can be mapped to, once again, the classification function. So the fully connected layer, it contains neurons that connect to the entire input volume, as in the ordinary neural networks. That means all the feature vector, whatever feature vector representation extracted through the series of convolutional layers, and in between there would be some pooling layers. But finally, they are converted into a feature vector form. So even if you get a two-dimensional or multi-dimensional array, a representation of the output from the feature extractor, they are rasterized, they are linearized to get converted into like a vector, like instead of two dimensions, it's a single dimensional vector. So this input volume to FC layer can also be treated as deep features, as I mentioned. And if the FC layer is a classifier, the input to FC layer can also be treated as feature vector representation for the sample. So a typical example of the deep neural architecture, this is one of the very first deep architecture which has shown the application, and you can see that publication is in 1998. Even that time the GPU processing did not mature in this regard. Data sets are also not that much, but still you see that all the concepts are there itself. And finally, around 2010, 2011, the present versions of neural network is coming with larger, with deeper network and other things. So this net is called LeNet, and you can see that it's a series of convolution. So this is a convolution layer, then there is a pooling layer, then again you have another convolution layer with that downsampled representation of the feature space. Then you perform another level of pooling. So these are, as I mentioned, these are fed to the fully connected layers for classification. So these feature vectors, they are converted into a linear form, into a linear array form of vector. So number of parameters, in this case, it is 60K, 60,000, about 60,000. So we have 2 convolution layers and 2 fully connected layers. And then number of floating point operations per inference was 341,000, and they have used sigmoid nonlinearity. Sigmoid function as nonlinearity. Now, this was used for document processing, actually, character recognition. It was demonstrated for that purpose. Now, there are certain issues regarding this, convolution, computations in the convolution layer, and some of those issues are addressed, and accordingly, this architecture also has evolved. So, first thing is that it has been observed that these computations, these computations can be done efficiently with smaller kernels. So, whenever there is a requirement of larger size kernel, you can equivalently, that receptive field you can achieve by a cascaded series of convolutions with smaller kernels. So that means one single convolution layer of a larger kernel, say 7x7 size of kernel, can be equivalently done. Equivalent means not the exact computations, but the receptive field can be covered by, say, 3 stages of 3x3 convolution kernels. So this is what I mean, stack of 3x3 convolution layers with stride 1 has same effective field as one 7x7 convolution layer. So it is deeper with more non-linearity. That is another advantage, that it is deeper because you have 3 layers, and also since from every layer you are introducing a non-linearity, so you are having more non-linearity over that computations, and because usually the deeper the model, better its accuracy. That is one of the advantage, but you should have a caution as a rider that it depends upon the amount of training data that is used for training the model. So if the data size is too small, you should not have large model, then it would be overfit. So you should have to check that part, whether it overfits or not. Then it has fewer parameters, though there are 3 layers, but if I add those number of parameters in each layer, that would come less than a single layer of a larger kernel size. So you can see that computations, it is shown that if you have a single layer with 7x7 kernel size, so the number of parameters is 7 square into c square. I am just ignoring the bias term for the neurons, and in this case it is 3 square c square into 3. So it is actually 3 into 3 square would be 27 c square, and this is 49 c square. So naturally this one is less than the 7 square c square. So this is just a typical example, and you can consider the same argument for any other sizes. Now, this principle is used in a particular type of network, which is also very effective and popular and used in various applications. This network is called VGG network, and it has there are several variations of this network depending upon the number of layers. As I mentioned, that it is a training data set, size of the training data set that should correspond with this kind of, should be appropriate for handling that many layers. So there are 13 layers, 16 layers, 19 layers, and each with 3x3 kernels. And there are other things that are descriptions are there. That means there would be pooling layer also, which we are not specifying here. You can get the details in the corresponding text which is discussing VGG network. Then the second issue which we will be considering here, the how to handle the scale in the feature representation. So far I have mentioned earlier also that scale is one big issue in feature extractor itself, and we know that multi-resolution representation of images can provide you some key, to solve that problem. Now, in this case also, what we do that we consider a similar kind of processing. That means we process at different resolution and then we can concatenate those features. For example, you consider this particular type of architecture where you can see that there are several convolution layers which are concatenated. Say one convolution layer handles, say when your input is 28 cross 28 cross 256, that means you have your size of your image here, for example, image or feature space, whatever you can say, it is 28 and 28, and there are similarly stack of such these things, and this is 256. So that is the kind of your input, which could be some kind of results from the intermediate processing in the feature space, and then it is fed to different kind of convolutional layers, and all are working in tandem. All are working simultaneously at the same level. Say one is 1 cross 1, 128. See, 1 cross 1 filter is very interesting. 1 cross 1 filter means that throughout the depth only these are processed. That means 1 cross 1 filter is something like the filter response is simply one dimensional, as if one dimensional impulse response. So you just take the dot product of these two, every pieces of depth wise pieces, and each one will be mapped to one value. So finally it will give you 28 cross 28 output. That is the activation map. But if you consider there are 128 such 1 cross 1 filters, so which means there would be 128 such filters like this, and each one will give you this output. So what would be the output in that case? You will get, this output would be 28 cross 28 cross 128. This one is 3 cross 3 cross 196. So you can see that here you are having larger receptive field, which is acting like a kind of if I consider low pass filter, you are smoothing with a larger task. Of course, you have to learn this. It is not, nothing is designated as low pass or high pass. When you learn it, certain characteristics would be there. So in this case also, we are doing full convolution, which means even the borders are also considered and the same image size is kept same. So as you understand that it is basically 3 cross 3 cross 256 kernel size, 3 cross 3 cross 256 kernel size, and there are 196 such different filters. So the output from this of size would be 3 cross, this should be same, it keeps the size 28 cross 28 cross 196. So here you get 28 cross 28 cross 196. Then we have similarly 5 cross 5 cross 96. In the same way, we are getting 28 cross 28 cross 96 channels. So like this, and this is 3 cross 3 max pool, which will keep the size as same, and you will get from the max pool itself. So it would be divided. It would be considering, and it is basically with stride 1. Though you are doing max pooling, you are not reducing, because when you are concatenating, you have to keep the input size same. So in this case, you have 28 cross 28 cross 256. So this is you are taking the maximum value from 3 cross 3 window, but with stride 1, that means with overlapping window. So you keep the image size same. So when we concatenate all of them, so concatenation means say this one will be an image, if I consider, of depth 128, not so basically these are all feature space, computed feature space. So this is stacked with once again another 196. All are of size 28, 28. So this will be stacked with, say, 196. Then there will be 96, stacking of 96 such plane. This is 96, and further there would be 256. So if I add all of these channels together after concatenation, your output size would be 28 cross 28 and so many number of channels. You just add them. So this is how you handle the multiple scale description. So you can see at different scales because of the operations at different scales you are doing it. But of course, the constraint here, as you can see, that we are keeping the image size same. Usually when you do some kind of multi-scale operations, we do some downsampling, but we are not doing downsampling here. But after that, of course, you can perform some operations. Now, this kind of computations is this kind of module is called inception module, and it is used in Google Net, where you have 57 layers, including 21 convolutional layer and one fully connected layer, and others are having some pooling and other things. Now, that was the second issue. The third issue, which we will be also considering in this computation, is the vanishing gradient problem. The vanishing gradient, as you understand, that when we are computing the gradient in the parameter space, that gradient of the error with respect to parameter, so we are computing using the backpropagation algorithm. Now, what happens that if it is a very deep network, those values becomes very small, it is almost zero. So then this computation is not feasible. Then everything becomes zero. So it is not going to perform any computations. I mean, it is not feasible. So it vanishes. So that makes a problem. So increasing the depth is an issue. If you increase the depth, then you have to take care of that particular thing. So for that, what trick has been considered, that instead of learning that function directly, that target function directly, why don't you learn the residual mapping? So residual mapping, so it is just schematically shown here. Suppose you are implementing, say this is your input x and this is your output, where the function is maybe considered as, say, fx, right? This function is fx. Okay. So what you are doing here in this architecture, you are learning the differential part. So if this is fx, now you are learning something, say this function is hx, you are learning, and then you are adding x, then fx becomes hx plus x. So effectively you are learning hx, which is the residual. So we call it residual part, because fx minus, you are learning, effectively you are learning fx minus x. You are learning hx, which is fx minus x, and this is called residual. This part is called residual mapping. So you are learning that, right? So in ResNet, that is another popular network, and you can see that number of layers are significantly increased. So earlier in BGG also it was 13, 17, 19, something like, but in ResNet it could be more than 100 also, 34, 50, 101, 152, and it has shown good performance there. So more or less those are the issues. The fourth one is basically handling the dynamic range of the input to a particular layer. Now, because your sample, like you are doing over a population, over a distribution of the training samples in that space, now this range can vary, and if you don't normalize them, then at different layers you may get it is very difficult to getting convergence. So for that, what usually we try to do, we make the ranges, keep the ranges put in some kind of normal zone. So we normalize the standard trick of normalization. So whatever statistical distribution you get, you are expecting as an input for every feature component in every feature dimension as in the field. So you take the mean and standard deviation of that field and normalize each field independently. And we call batch normalization, because with respect to a batch, you can find out that what are those values are coming, and for the next batch, you can use this normalization. So it starts, you can start with any particular initial values and then you can update them and you can proceed with that. So to make Gaussian activation maps improves gradient flow through the network and allows higher learning rates. So these are certain advantages and reduces the strong dependence on initializations. It's a form of regularization, as you can see, and it is usually inserted after fully connected layer and convolution layers and before nonlinearity. So this is how it is done. So just it has been implementation, as I mentioned, that use the mean and standard deviation, and then you can transform the resultant output operation by scaling and translation by parameters of A and B and learned by the gradient descent algorithms. So during testing time also, running averages and SDs of activation maps used along with learned parameters A and B. So we learn these coefficients A and B. So it is not only just simply normalization by subtracting mean and dividing by respective standard deviation. So there are certain parameters what we used to do. So that is scaling and translation parameters A and B. Oh, these are acting like mean and standard deviation. And then for the robust computation, robustness, because in the training when you do, if you consider all the nodes precisely working, and then there might be an overfitting problem. So to handle that, what we used to do that while training itself, we randomly drop some of the nodes and train the network to get the as good as possible, optimize the node. So temporarily removing it from the network along with all its incoming and outgoing connections. And to regulate overfitting, that means you set the incoming input as 0 there and don't update them, set them in that forward processing. That's what you do. And then simulates learning sparse representation in hidden layers. So retain output of a node with a probability P. Sometimes we also do in that way. So typically within 0.5 to 1 at hidden layers and 0.8 to 1 in visible layers. So when we learn weights with dropout, the way you can do that, weights become larger due to dropout, needs to be scaled at the end of training. A simple heuristic is outgoing weights of a unit retained with probability P during training and multiplied by P at the test time. So that is a randomness when you can consider sometimes ignore the weight and you take the weight. So the probability P could be very high naturally, and with a small probability you drop that weight. And scaling may be carried out during training time at each weight update. No need to rescale weight for the test network. So finally, just to summarize about this deep neural architecture, training steps are the same as the training of any artificial neural network, which means you should preprocess the training data set. Like you can normalize the data, you can decorrelate data, and you can whiten the data, right? These are the transformations. For decorrelations, you try to make the covariance matrix, you make the diagonal, and whitening it should be identity covariance matrix. So, and then you subtract also, you should subtract the mean. So that is the kind of normalization of your data set. So whenever you get any test data, you have to perform with the similar, you observe those transformation parameters, use those parameters to bring into that normalized form, and then use it for test network. So some of the other thing is that since you require a large data set, sometimes your data may not be sufficient. So there are some tricks regarding augmenting data by doing some transformation on the input data itself, and because the levels have remained same, but you just transform, say horizontal flipping of the images, random cropping, and on scaled output, do some color jittering, add some distortions, any other kind of transformation. So that gives you another input sample derived from the given training sample, and keeping the levels same, you use it for training. So that would increase the robustness. And then weight initializations, there are with some methods, there are also approaches, and then you train the network by update of the weight parameters. There are a few training tips which also we should consider, like we should start with small regularization and we should find learning rate that makes the loss go down. Then it can overfit very small portion of the training data. So what you can do, you can train first few epochs with few samples to initiate the hyperparameters. Now, a big gap between training accuracy and validation accuracy, then it is overfitting, as we know that is the definition. Then what you do, you increase the regularization term. That means you penalize the larger model and again you fit. And if no gap, then you may increase the model capacity. So if there is not a gap, so it may cause underfitting. So you may go ahead with the model capacity. So with this trade-off, you have to come up with certain architecture. Right. Now, another thing which is very often used, we use the transfer learning process. Basically, the idea is that you have trained a network with certain data set. Now, for a new problem, you have another data set. Now, data set characteristics, data set format remains the same. So, what you can do that with that data set, if you want to use that network, instead of starting from scratch, use the whatever weight configuration is there in the trained network and then fine tune it with that data set. So, that would give you better convergence and also better performance. So, this is called, since you are transferring the learning from one domain to another domain, so we call it transfer learning. So, pre-trained models can be initialized, as we mentioned, for CNNs at the early stage of training. So, just to give one example, suppose you have you see that these are copies of the same network architecture. Now, the leftmost network architecture, so we train on data set 1, and then we would like to train on smaller data set. So, what we can do, that trained network on data set 1, we keep some of these layers as frozen. So, for example, most of these things are frozen. That means we don't want to update those weights. Only we are updating the FC3 layer here. So, you see that your training becomes faster and also it converges to that. Because we have a smaller data set, we are not tuning every parameter there. But if you have a bigger data set, what we can do, you can take a few more layers. It's like you can freeze only up to this level, up to these layers, and all other layers, like all other fully connected layers. So that means the whole classifier itself you can train, but they are initialized with the initial values of previous only trained network. So you can get here, you can use lower learning rate when you are doing fine tuning, because you are expecting your convergence should be near about point. So we are not going to deviate much from that. So with this background, let us start. We have considered the object recognition is mostly, as I said, that with the supervised learning framework, primarily object recognition is addressed using this network. But there are various other kind of tasks which are also performed and under the same framework. So one of the thing would be not only object recognition, we can also perform localization. Localization means that consider this particular image, and you can see that in this image we have detected the dog and also its position. We have detected a person and also its positions, and all these things are something like confidence. How confident is your classifier? So when actually this network or this model, the output of this model, it is giving several things. It is giving a bounding box in the image which is localizing this object. Then of course and also a confidence score that there is an object. Also there is an object for certain class, that can be a confidence score, and the class of the object. So many informations it provides using the same network or system. So this problem is called recognition and localization, both this task is cut. So what it predicts, as I mentioned coordinates of bounding boxes of objects and also class probabilities. So one approach could have been that you perform two-stage processing, like localization and then recognition. So when you are localizing, now we call it, you propose certain reasons. So we say randomly you are considering certain bounding box and you are saying, okay, this may contain an object. Of course, no, that is not a very efficient way. You have to do some more, apply some more heuristics. Suppose you have some kind of handcrafted way, or I should say classical way of extracting regions of possible objects. Then those region, we call them candidate region or proposed region. So there is a term called region proposal. So this computational model, it is extracting the region proposals, and each one is used in a trained classifier. So this classifier is actually your deep neural architecture, and where it will say that which class it is with some probability value. So this is a two-stage processing. First, region proposals are predicted, and each region proposals are used for this classifier. So there are different solutions are provided based on these two-stage proposals. Say pre-CNN, so before deep neural architecture or convolutional neural network used the standard classical approaches, like used region proposals, extract features, and then you classify. So there could be various kind of classifier, like linear discriminant functions could be a classifier. But in the CNN era, that means deep learning era, say after 2011 or 10, so region proposal still remains as a region proposal. So in pre-CNN, it was exhaustive. That means every box you are testing, very computationally intensive. But in this case, you are making more heuristics, you are making more intelligent guesses. So you propose those regions. That is once again a classical approach you are following, not the deep learning based approach. Any kind of image processing operations, computations you are doing. And then you perform the feature extraction only from using CNN. That means that from the pre-trained network, use the feature extractor part. Then that feature is fed to a classifier. Again, this classifier is based on any classical machine learning based classifier. So for example, linear SVM. Another version, another improvement of this architecture, now each one is giving better results. That's why it is shown in this way. It is also performing region proposal separately and by a way which is a bit classical way. But then the whole thing, feature extraction and classification, as we discussed, it is using a deep neural network. So that is some improvement is there. And in faster CNN, whole thing is under deep neural. So it also predicts the region and finally it classifies. But we call it two-stage process because still this cascaded part is there. You predict the region and then you do that thing. Now there is a single stage processing where you perform end-to-end. The last approach is something similar, but here this is more direct. That's why we mention it separately. And you see the name is very interesting. You say you only look once, as if just the image is given. Immediately, it will tell that where is the dog, where is that the machine is acting like a human being. So the abbreviation you can pronounce as YOLO network, which is very popular for doing various tasks. So what it does, it divides the image into S cross S non-overlapping grid. S is some hyperparameter. For example, you see that all boxes, these are grids of equal size. Of course, my diagram is not that uniform, but assume these are all equal size. Now consider for each box, you predict some bounding box around that, centering that one. So which means the position, and also you are considering its width and height. So that would give you the bounding box, center of the bounding box and width and height. That may be the positions. And also a confidence score you are giving. So you can generate a number of candidate bounding boxes for each grid itself, and then you classify the one which has the maximum confidence. So you get a classification probability vector for several classes. Suppose there are 20 classes you get. Here, for example, we have some representative classes like dog, bicycle, car, maybe road, maybe tree. Those things are there. You can have many other classes. So that's what for each grid predict B boxes containing objects with confidence score. So this is some processed result. So some of those bounding boxes are shown. Some of having confidence are shown with thick boundaries, and those are mostly used with higher confidence. You get the softmax probabilities of object classes using a pre-trained network for the box with maximum confidence. So finally, you may get a result like this. As you can see that this box contains the dog. This is yellow box contains the respective cycle. This is car. So in this way, you get both localization of the object and also its class. So we have end-to-end training for both predicting bounding boxes and object classes. And final output would be, as you understand that for each grid, you are predicting this. So for each bounding box, say there are B number of boxes, there are 5 quantities like the position, coordinates, and then width and height, and also the confidence score. And C is the number of classes. So you get that many tensor which is presented in the form of array. That is the kind of form of your output. So its implementation is again simply a series of convolution layers coupled with some max pooling and followed by a few fully connected layers. So typically, for example, for image size of 448 cross 448, the value of S is 7, which means the grid is 7 cross 7. The number of bounding boxes, which is indicated by parameter B, is 2, and C is number of classes, which is 20. And in the loss function, you have to consider all these components of predictions, like you should have localization loss on the coordinates which are given by the ground truths, then confidence loss, that is also either 1 or 0 if it contains object or not, through manual annotation you can get, and classification loss. So these are the loss, and in this case particularly, all of them use MSE for the sake of convenience, though you understand that classification loss is not ideal for expressing in MSE. The last one, or I should say not last one, rather another kind of task which we will be discussing using this kind of deep visual learning, that is semantic segmentation. So here semantic segmentation, the task here is that you label each pixel in the image with a category. So this is a dense classification problem. Each pixel is labeled, and by that you get a segment. So we don't differentiate instances, rather only care about pixels. So when we say an object, it's a collection of pixels denoting a single object. But in this case, pixels are denoting a class, and from there you have to infer about the existence of a single object. So building blocks of CNNs, like you use convolution, you use downsampling, and you use upsampling. Let us understand how we can perform upsampling. And as I mentioned, there are two techniques. One is called max unpooling. Another is basically using upsampled convolution. So let us understand these two computational process. So for unpooling, first let us consider the pooling result itself, which we have discussed. Suppose this is the respective feature channel, and from where you are performing 2 cross 2 unpooling. So 2 cross 2 max pooling. So when you are doing max pooling, you are reducing the size of the image by considering 2 cross 2 partitions, non-overlapping partitions of each part, and from each partition you are taking only the maximum value. So from this partition, this is the maximum value, and that is what is forming here. Similarly, from here you get the max pooled value, this one 6 here. So similarly you get 7 and 8 in this case. So you see that from 4 cross 4 image array, you are getting 2 cross 2 by 2 cross 2 max pooling operation. Now, the reverse operation, which is called max unpooling, that can be performed in various ways. One way could have been that you can simply expand this each cell, because 2 cross 2 unpooling means this each pixel corresponds to 4 pixels and one of them is 5. So, by convention, if I assume say this position would be the position and then rest other things will be 0. So, we can accordingly we can form a larger array for this unpooling, where every pixel value is stored in the leftmost and topmost position of the corresponding 2 cross 2 expansion of a pixel, and then you get a respective unpooled image. But one of the thing is that sometimes if you are performing the operations within the same process, computational process, so it is easier to remember also the positions of pooling during this max pool operation, which means say this max pool operation, we can have the corresponding indicator array where each positions are also noted that from these positions this max pooling operations have taken the value. For example, this is the position, so we indicate this position by 1. This is the position, say this position is indicated, this position is indicated, and this position is also indicated, and rest of the positions we will put 0. So, it is a binary value. 1 indicates the positions from where the pooled value has been considered. So, this is the position here. So, in that case, what we can do that instead of taking by default these positions, that means the topmost and leftmost positions, we may consider, for example, with respect to this, then we can just simply use the position indicator to replace that value, to set that value, and other value would be 0. In the similar way, this one would be 0 and this is 5. This is already 1 and this is 6, and this position is 1 at this location. So, we will put this one as 8. So, this becomes your max unpooling, but for that you require this indicator array of the positions. So, this is what is the process of max unpooling operations, and you are upsampling the array by inserting zeros. Later on those things can be filtered and you can get the upsampled feature array from there. So, I will come to that next stage, but let us once again summarize these computations with a clean image. So, these are the pooling indices. So, we call indicator array is basically pooling indices are recorded, as you have noted here, that for 5 the pooling index location is this position of the array. In the same way other things. So, this is also propagated throughout the computational blocks, and we remember this, and when we perform the corresponding max unpooling, so we can say, suppose we get some value A, B, C, D after processing. So, you are not expecting that you will return the same value. After processing, these values are changed. So, A, B, C, D will be the value, and then you want to do max unpooling using these pooling indices. So, your resulting computed array would be this one. So, this is the process by which you can do max unpooling. Now, let us consider that how again the other technique, upsampled convolutions, how you can perform. In upsampled convolutions, actually what you do that first, like unpooling, you insert zeros in the respective cells of expansion. So, say again 2 cross 2 upsampling you are doing. So, each cell should be, each location should be upsampled into say 4 pixel locations, and we consider this by default once again take these positions, the same step what I mentioned. But additionally what you are doing after that, there is a kernel, there is a filter which you are with which you are convolving it, and you are getting the resulting image, resulting upsampled value. So in this case, 2x2 upsample, as I was mentioning, that no, first you create this one and then you apply a filter. Suppose you have a filter like this, so you can note that it's a kind of low pass filter. If I add all these values like 0.4, so it is 0.8, and then 0.2, it is 1. So this is a kind of low pass filter. So you are basically performing the convolutions, including assuming the border elements and zero padded border that. So resulting image after convolution, for example, if I want to say this is the resulting array, suppose let us consider any particular location, let us consider this location. So what happens that during convolutions I have to multiply these weights. So since these are all 0, only I am multiplying the 5 with 0.05, 6 with 0.05, 7 with 0.05 and 8 with 0.05, and which will give me the value of 1.3. So in this way you are just performing simple convolution what you have done. So in your upsampled convolution process, whatever thing you get, so if you get A, B, C, D like that, or those values are convolved and you get the resulting operation. So in this way you get the larger array size, upsampled array size. So in the case of semantic segmentation, we use fully convolutional network. It is fully convolutional network because all the layers are convolutional layers. Of course, there are pooling layers in between, as you have said, and then there would be also layers for upsampling and unpooling. But all are convolutional layers primarily, and there is no fully connected layers. So your objective is that your input is an image, even your output is also an image. So you have the same kind of array structure, or output could be also a tensor of certain array structure. And in this case we perform dense prediction. That's why every position of your input image, every pixel location, you have a prediction of its class. That is the purpose of semantic segmentation, because there would be certain set of classes and every pixel will have a probability of its belongingness to a class, and from there you determine the respective semantics of that particular pixel. So the procedure by which we do it, we make a intermediate representations by accumulating the features, by computing features. So it's a downsampled, there are two parts. One is the downsampling part, which you call usually the encoding part. And then after that we perform upsampling, and upsampling can be done in different stages. It can be done stages, it can be done also in such single stage. And when you do upsampling, after upsampling images, what we actually do that each pixel is processed by a 1x1 filter. So in the upsampled image, you may have number of channels. In the output you may have number of channels, and then there is an 1x1 filter. So finally, for each pixel you get, suppose you get 1x1 cross k. That means each one is 1x1 filter with k channels, and each one will give you some values, and this can be converted into a softmax probability, and each channel is corresponds to a prediction to a particular class. So that is how the semantics are associated with the pixel, and this is what is mentioned by the providing softmax code at every pixel. So number of channel of the output layer should be equal to the number of classes that we have considered. And in this case, since the ground truth is available for each pixel locations, you can use cross entropy function as a loss function for training the network. So this is one example of how semantic segmentation could be carried out. As you can see that what we are doing here, we are doing first the respective features, images, the features are extracted and then downsampled, and then there is a upsampling process. and from there you perform that pixel wise prediction. Now size of this and this array, its channel size should be the same, so that each pixel corresponds to that class. This kind of network, as you have seen that in the one stage you are extracting features and representing the image with certain set of features, and then again you are doing upsampling and you are again getting back another kind of representations of similar array dimension, which may not be which may not be the same image, which would be related to the image, like class predictions. We call one part is encoder, which is encoding the images into its feature space, and then from feature space you are decoding it to your desired computational space or resulting space. So that is what it takes an input image and generates a high dimensional feature vector encoder and aggregate features at multiple levels. Whereas decoders, it takes that feature representation and then aggregated by encoder at multiple levels you decode, and then semantically project the discriminative features learned by encoder onto the pixel space. So that to get a dense classification. So this is a very typical encoder decoder architecture which we considered, and you can see that these stages are the downsampling operations with pooling, different kinds of pooling, and then you are also propagating pooling indices in the same. As I mentioned, when you do max unpooling, these pooling indices will perform the respective operations. Then again you perform the filtering to get the next level of representation. So in this form, and finally this is output. There are different classes, and use 1x1 filter, as I mentioned, to get the class probabilities of the output. Now there is another type of architecture which is also very interesting, and which we called UNet, and it is inspired from the wavelet analysis, where you know that in wavelet we have already discussed that you can have the dyadic decomposition of wavelets, and again you can synthesize them, which means that in this case, as you see that given an input signal, you are using the filters to get the high frequency components, which are details, and then the low frequency, which are called approximations, and then again downsample them. And once again, this component is also next level, it can decompose into details and approximation, and then this quadrature mirror filter concept, by which you can fully reconstruct the signal what is received at this end, in this case here, and then again you upsample and you can fully reconstruct the signal with appropriate filter design. Now when you are using wavelet analysis and synthesis, you are using a standard using the filters are all analyzed using a theory by which you are already, these filters are determined. But in the learning mechanism, we almost use similar kind of structure with much more generalized model architecture in the generalized architecture form, and then learn those parameters. So if I translate these operations in the form of encoder decoder in the unit architecture similar to this analysis and synthesis, you can see that your input image, it is passed through several filters in convolution layers, and then one of them is, so this representation it is downsampled, and then again passed through several layers, again it is downsampled, and this one is directly is concatenated, like in the previous case, as I mentioned, that the high frequency component is going. So it's just simply concatenation what is this used. Now this one is upsampled as it is done in the case of wavelet reconstruction at this stage, and then this concatenation takes place here. So and then it goes through the processing, and these are the filters, again there is an upsample filter, and finally you get the result. So there is at the final layer you get 1x1 convolution used to map each feature vector to the desired number of classes. So this is what is used there. You use usually the cross entropy loss function there. So some examples, this unit has been found to be very powerful, particularly in various other domains, including the results where it was shown first in segmenting the cellular components here. So you can see that these are the ground truths what are given here, and these are the computed one. So the yellow border is the corresponding ground truth, and the computed one are the colored parts, so which are closely following the ground truth there. So little bit of variations of this architecture, the same form, in general we can call an encoder decoder, and it gives you a very powerful model. Say for example, you can see that even it can reproduce self-reproduction system or self decoding system. That means we call it rather it is basically called auto encoder, like it is encoding it and then you are decoding it, the same image. And here of course loss function you are using the mean squared error loss function we are using. Now this application, this has several applications. Like first thing, you understand that to train this network you do not require to annotate it, because you are producing the same image. So given any input image, you already got the desired output. So that's why we call this kind of learning as self-supervised learning. But it could be in various other form. For example, suppose this one is the black and white image and or gray level image, and this is colored image. So you are converting a gray level image into a colored image. So that also, that kind of self-supervised learning, because you can always process a colored image to a black and white image and use that black and white image as the input and get the colored image. So given any arbitrary black and white image, you can get the colored image. So these kind of applications are also possible. Similarly, super resolution, another application, like you can interpolate the images. If you know the higher resolution, you can always derive the lower resolution image. Now try to solve the reverse problem. Input is your lower resolution image and get the higher resolution image. So in this way, you can generate your data set and you can train the encoder decoder architecture to solve the problem. So just to summarize, what are the things we have discussed under this topic, that we consider the deep architecture which works in the same principle of artificial neural network, and the characteristics is that it has a large number of hidden layers and it has a large number of weights, of course. That means very complex model with millions of weights in some cases. And you should have, so one of the model which is mostly used in this case is convolutional neural network. Primarily, convolutional neural network is considered as the kind of basic module or base model of doing the feature extraction part, learning the feature representation from the images processing, and then even for synthesis, as you see in the decoding part also convolution is used, and otherwise for classification part use the fully connected layers. So in convolution neural network you learn filter weights, that is one of the objective, and it has the feature of sharing of weights. So architecture becomes simple than the fully connected layers architecture. Description becomes simpler. There are two types of layers under these convolutional neural networks, what we have seen. One is convolutional and the other one is pooling layers. And there are two stages of processing. One is that feature extraction, and if you want to solve the classification problem, then there is classification. So with this, let me stop here, and I hope you have understood certain parts of deep learning based approaches of visual processing, and thank you very much for your patience and listening.